Database normalization. You might have heard of it, you might be confused by it, or you might have no idea what it is. In this video, I'll explain what database normalization is, how it helps your database design, and show an example using a realistic database. By the end of the video, you'll have a solid understanding of what database normalization is. And if you want a quick reference for everything we cover in this video, you can get my database normalization cheat sheet from the link in the description. Let's say you have a table in a database. This table stores information about subjects that are available in a university or college course. There are two records shown here. They both have the same ID value, which indicates they are the same subject. However, the name of the subject is different. One says Chemistry 101 and the other is called Introduction to Chemistry. Are they the same subject? Are they different? Does one record replace the other? It's hard to tell. This issue is just one of the many issues that can occur in a database. It's easy to blame the application or the users for this kind of problem. However, this problem of having two different names for the same subject is caused by bad database design. We can design tables in a flexible way, allowing all kinds of data to be stored. However, without proper design, we can end up with issues with our data like this issue or much worse. How does this relate to database normalization? Well, database normalization is the process of organizing and designing your database so it's efficient and consistent. And if we follow the process of database normalization, we can avoid these kinds of issues in our database. It makes life easier for us, our team, and the users of whatever application or solution we're working on. Without database normalization, you'll get contradictions in your data, like a subject having two different names or a student having two different birth dates. And with normalization, you will also find it easier to make updates to the data, as you don't need to make updates in many places. You'll also reduce the chance of breaking your data if you insert, update, or delete rows. So that's why database normalization matters. Let's start with an example table and go through the normalization process. We're going to continue our theme from earlier on university courses and use a table called Subject Enrollment. This table captures a list of all of the enrollments that have happened for a subject, which is where a student joins a subject. We have a few columns here: student name, which is the name of the student email, the name of the subject within a course, the name of the lecturer, the office location of the lecturer, the semester of the subject, and the classroom that the class is in, and the enrollment date of the student in the subject. There is a lot here. Let's take a look at some sample data for this table. We can see a few things here. We have 4 rows, but rows 1 and 4 show the same student, John Smith. We have some columns with multiple values in the same row, like these subject names and lecturer names. We've got many other issues with this data, but we'll look at them as we go through this normalization process. So what do? How can we improve this? The first step in the normalization process is called first normal form. To achieve this, there needs to be no mixed data or repeating data. What does this mean? Here is our sample data again. The mixed data or repeating data means that there is more than one value in a cell or more than one value in a column for a single row. The subject name column for the first row, John Smith, has 2 subjects in it. A row must only represent one piece of information, but there are 2 here. This does not meet first normal form, and this is something we need to fix. We can say the same thing for the other columns of lecturer name, lecturer office, semester, classroom, and enrollment date. So how can we fix this? We can adjust our table like this. We have the same columns as the original example, but we have moved the values from rows that had 2 values into their own row. For example, the first 2 rows were originally in a single row. Now they are in separate rows, 1 row for each subject enrollment. The first row is for the first subject, and the second row is for the second subject. Each row now has only 1 value in each of the columns. We did the same thing for all of the rows. Now there's one more thing we need to do to this table to make sure it meets the requirements of first normal form. We need to have a way to uniquely identify a row. We need to be able to find a single row in this by specifying some data and getting a row back. If we want to get the enrollment record for John Smith, we would actually get 3 rows because there are 3 records. so we can't use the student name to identify the record. What about the student name and subject name? Well, that could work, but it's possible for a student to enroll in the subject more than once, so it's not unique. We're trying to identify a primary key here, which is a way to uniquely identify a record. There are generally two ways to do this. You can find an existing column or a combination of columns and specify those as a primary key. In this example, it could be student name and subject name and semester. This approach is called a business key because it uses existing business data. The other approach is to create a new column that has the sole purpose of being the identifier for the record. That's called a surrogate key. Either way will achieve the goal of first normal form, but my preference is to use a surrogate key, which is to create a new column. So we'll do that here. We add a new column called ID and give it a unique number. This is our primary key. We have now achieved first normal form. First normal form is about the basics. No repeating data, one piece of information per cell, and every table needs a primary key. This is what the entity relationship diagram would look like for our table. It's pretty simple at the moment. We only have one table with a range of columns. This will get enhanced as we go through the normalization process. If you're finding this helpful, grab my database normalization cheat sheet from the link in the description. What's next? Second normal form. The rule for second normal form says that every non-key column must depend on the whole primary key. What does that even mean? Let's take a look at our sample data to explain it. In our data, we have a column called lecturer name. This represents the person who is lecturing the subject or teaching the subject. Our table shows a list of subject enrolments, as you know. The problem here is that the name of the lecturer depends on the subject and not on the enrolment. For example, Mrs. Joan Field is the lecturer of the subject Introduction to HTML. This lecturer name is a property of the subject and does not change for each enrolment. So the lecturer is not dependent on the enrolment. Why is this an issue? There are three problems with storing data like this. Let's say we wanted to add a new subject with a new lecturer to our database. We haven't got any students enrolled yet. But with this design, we can't store anything about the subject or the lecturer until we have an enrolment. We could add a kind of dummy enrolment record where everything else is null, but then we're just making up data. This is called an insert anomaly. The second problem we could face is when we want to make changes to a record. Let's say the lecturer for Introduction to HTML changes. We would have to update every row that matches the subject of Introduction to HTML. There is a risk that we would miss a record, perhaps if there is a spelling mistake or some other issue. If we don't update all of the records, then the data is no longer correct and could be confusing. This is called an update anomaly. The final issue can happen if we delete a record. If we delete this record for Michael Brown, who is the only student in the subject of Introduction to CSS, then we lose all record of the lecturer Mr. Chris Smith and that he teaches that subject. We shouldn't lose this information if we delete an enrolment. We should be able to keep it. This is called a delete anomaly. So how do we fix these issues? We can move this information to a separate table and then link these enrolment records to the new records we create. We start by creating a new table called subject. We have an ID, which is the primary key. We have the subject name, the lecturer name, and the lecturer office, which we moved from the subject enrolment table. Notice how we only have one record for each subject here, even though there are multiple enrolments for the same subjects. We only need one record for each subject. Back in the subject enrolment table, we remove those columns that stored the subject and lecturer details and replace it with the subject ID. This ID is called a foreign key and it points to the ID in the subject table, the one we just created, for the related record. So we still record which subjects each enrolment is related to in our database. It's just in separate tables, and this is okay. Here are the two tables, subject enrolment and subject. We can match the two tables on this ID here, so we will be able to see the details of the subjects. This can be done in SQL using a concept called a join, and it is a very common thing to do. Now we can and should do the same thing for the student information in this enrolment table, which is the student name and the student email. We can create a new table called student with an ID and these two columns. We link this student record to the subject enrolment table in the same way, using a student ID column as a foreign key. Here is all of our sample data, separated into multiple tables. This meets the second normal form rules. We're starting to make some good progress and improve the design of our database. Here is an ERD with the 3 tables. It's a different way of seeing the database and how the tables relate to each other. Now that second normal form is met, let's move on to the next step. The next step is third normal form. The rule for this is also a bit confusing, but I'll explain what it means and how to meet it. Third normal form says no transitive dependencies. That means a non-key column shouldn't depend on another non-key column. Or we need to make sure that any column that is not the primary key only depends on the primary key and none of the other columns. The main reason is to prevent the update anomaly issues we identified earlier. If something about our data changes, we should only be able to update it in one place. How can we achieve this? We can go through all of our tables and see if any of the columns in the table depend on another column that is not the primary key. We'll start with the subject table. In this table, the lecturer information does not depend on the subject. A lecturer will exist regardless of the subject existing. So we should move this to a new table and then relate the right lecturer to the right subject. We can create a lecturer table like this, which has an ID, the name, and the office. We update our subject table to link to the lecturer ID as a foreign key. We can say the same for the classroom in the subject enrolment table. A classroom exists separately. It is not dependent on subject, so we can move it to another table. We create the classroom table with an ID and the classroom code. This will also allow us to add any extra details about the classroom, such as the type or number of seats or location. Here is the ERD for our database so far. We have a few extra tables and it now meets third normal form. Now every column depends directly on the key and not through another column. Many database designs stop at third normal form as it's usually enough, but there are a few extra steps or normal forms that are available. The next one is called Boyce-Codd normal form, or BCNF. It can also be referred to as 3.5 normal form. BCNF is a stricter version of third normal form. It handles rare cases where you've got overlapping candidate keys and need to follow a similar process as we did for third normal form to move attributes to separate tables. You probably won't run into it often, but if you follow the steps of separating data to a different table as we did in third normal form, you'll also meet BCNF. The next normal form is called fourth normal form. This step is all about something called multi-valued dependencies. That sounds complicated, but it is a simple idea. If two pieces of information are independent, don't put them in the same table. Let's enhance the concept from our university example before. Let's say we want to capture more information about subjects, such as the textbooks that are used for the subject, and some guest lecturers who teach parts of a subject but are not the main lecturer. Here is what our table could look like, which we've called subject material. We can see a textbook title and a guest lecturer for this subject. However, the list of textbooks and the list of guest lecturers are actually independent. They are not related to each other. By combining this data into a single table, we have created unnecessary combinations. If we need to add a new lecturer, it means adding new textbook values. How can we fix this? The way to fix this is to split the table into two independent tables. One for the textbooks for the subject, and one for the guest lecturers for the subject. You might think this is similar to third normal form, and it's close. The solution is generally the same, which is splitting tables, but the scenario that causes it is different. Now we have two different tables instead of a combined table with two different pieces of information. Now textbooks and guest lecturers can be managed independently. Adding a new lecturer doesn't mean duplicating textbook data, and vice versa. We have now met fourth normal form. Fifth normal form is about avoiding unnecessary decompositions. Sometimes a table looks fine at fourth normal form, but still allows data inconsistencies if you try to represent multiple relationships in one place. Here's an example. Suppose we want to track which lecturers teach which subjects in what departments. This might seem okay at first glance, but this table actually stores three independent facts. First, it's storing which subjects belong to which departments. Second, it's storing which lecturers belong to which departments. And third, it's storing which lecturers teach which subjects. It's storing information about how each of the three columns are related to each other. If one of these things change, there's a risk of inconsistent data. For example, Look at the third row for Maths and Dr. Lee for Subject 2. If we change the department from Maths to Computer Science, does this mean the subject has changed departments, or the lecturer has moved departments, or something else? The way to fix this is to split these pieces of information into separate tables that capture each relationship clearly. We have 3 tables, one for department, one for the lecturer and department, and one for the subject and lecturer. By splitting the relationships, we prevent errors. If Dr. White moves to the Maths department, we only update the lecturer department table. The database can reconstruct all valid combinations by joining these tables. There's no risk of invalid or missing rows. Here is a recap of the different normalisation levels we covered. We covered first, second, and third normal form. We looked at Boyce-Codd normal form, then fourth and fifth normal form. Each normal form builds on the previous one. So to be in third normal form, you also have to meet first and second normal form, for example. If you found this helpful, grab my database normalisation cheat sheet from the link in the description. And if you want to see another example of designing a database, check out this video where I design an IMDb style database for movies and everything that relates to it. Thanks for watching.